Yeah, hello and welcome to PML School. Today we are continuing with our comparisons of NONMEM and NLME models. And we also continue with model validation. So last time I showed you how to set up and run bootstraps for both NONMEM and Phoenix NLME. And today we will focus on the visual predictive check VPC. As a model example, we have a mixed absorption model, and that is not a simple model. It seems like with all the previous PML School webinars, we've ran out of simple examples. So this is a rather complex model, but nevertheless, I mean, we will go into details of the code, and you will see the comparisons between the NONMEM code and the NLME code. And please be reminded that we are just focusing on the practical things of, running these models. So we won't get into details around theoretical concepts. And as always, while I'm going through the presentation, if you have any comments or questions, please use the Q&A panel at the right-hand side of the WebEx console. So here's our agenda for today. As usual, we start with a brief description of the model, and then we look at some plots of the actual data to explore, and then we also compare the two inputs for the NONMEM and the NLME model. This is a study data, and next we talk the laser pointer. Then we go into the details of the NM trend code for NONMEM and the PML code for the Phoenix NLME model, line by line, which is then followed by the demo, the first demo, where I just show you how to set this up and run this. And this is then continued with the validation, VPC for NONMEM and for the Phoenix, and again showing this in a demonstration. Finishing with a summary and a Q&A. So what is our model about? It's a two-compartment model. We have mixed absorption first order and zero order, and it is a separable absorption. And the study data have doses ranging from 1 to 800 units. So in here our structural parameters, quite a lot, as you can see. We have clearance, central volume, peripheral volume. We have the flow between the two compartments. We have an absorption rate constant. We have two bioavailabilities, and half maximal dose for the two absorption processes, and the duration for the zero-order absorption process. For the error model, we have a power error model in this case that we apply. You will see the details when we come to the code. And as structural parameters, for these three parameters, we have between subject variabilities calculated, and we assume log normal distribution for all of those three. Fixed effects, since there are so many, I mean, we'll wait for the code details when I show you what initial values we will set for those. For the random effects, since we only have three, we put for the eta on clearance 0.2, eta on volume 0.3. This is on the central volume, and eta on AF50 0.1. And as usual, we stick to the default engine, which is FOC ELS. So coming to this is a profile of the first subject. This subject received 2 doses, 1 unit and 30 units. And from this low dose profile, you see, you've got an absorption, and then I guess this is a log normal scale, a semi-log plot. See there are 2 slopes, so we have 2 compartments. This is at 30 units dose, looks familiar, but with these 2 profiles, you cannot really identify the You may also refer to other plots like AUC over dose for the different dosing regimen. Absorption. Okay, this is input. Sorry, this is getting a little bit small because of this wide input table. But for the input, we have already a very complex example, and in this case, we want to stick as close as possible to the NONMEM definitions. So we try to not change the column names for these two inputs, and you can use them right away in this. So this, starting here with the ID column, the subject identifier, the time, and the amount. This is a dose amount, and since we have two absorption processes, so we need to distinguish between the two compartments, and this is done in NONMEM with the CMT, the compartment column, where you identify which compartment receives this dose. This is differently handled in Phoenix NLME, where you just split up the amount column into amount 1 and amount 2. So you don't need a compartment column in this case. Then you have a treatment column that you have the same here in NLME. You have the DV column, dependent variable. This is the actual observations, the PK, the concentrations. Same here in NLME. Then we have a rate column, and this you see for the second compartment. This has a value of -2, and that this specifies the zero order absorption, and that is defined with the duration. So this is how it's set up in NONMEM. This is explicitly coded in the PML code in NLME, so we don't have that. Then we have the EVID column, event ID, which is 1 for dose and 0 for observations, and 4 if you want to reset the compartments. That we can also use in NLME, as well as the MDV column, the missing data value column. Whenever there's a dosing record, it's obviously a missing data record, and for all the zeros, these are observations, and the same is being done with the NLME input. So that's about the input. Now coming to the code, so you see on the left-hand side the NM-TRAN code, and on the right-hand side the PML code, and we have chopped it up into those pieces that belong to each other. For example, you start with the NM-TRAN code with subroutines, AD1, 4, and trans 4. So this is a pre-specified model. In this case, it's model 6. It's 2 bioavailabilities, Emax of dose and Emax 2 of remaining amount from F1, and you specify the same in NLME, in Phoenix NLME, using, for example, here's a dose point. You have 1 for the depot and 1 for the central compartment. So this would be the gut, and this would be the systemic blood, and so we specify bioavailabilities, F1 and F2. For these two compartments, and for the central compartment, we also have specified the duration for the zero order absorption. Then these are the differential equations that you need to set up in NLME. So this is a typical absorption compartment with an absorption rate constant. This is for the central compartment, and you see it uses a micro constants that defines the flow between the compartments. And then here's a differential equation for the peripheral compartment. In this case, we set up dose as a covariate so that we can directly read this into the code in the data file. So you don't need the dosing records. This is now defining the structure parameters, and you see we have quite a lot. And in order to not to confuse you, or to confuse you only to a minimum because of this, busy text here. We kept to the same definition of parameters. So these are the structural parameters defined in NONMEM: clearance, central volume, peripheral volume, flow, absorption rate constant, and the two absorption processes, the parameters of the two Certara absorption processes. And they are then defined with this typical product of theta, the fixed effects, times e to the power of eta, the random effect. And you see this is defined analogously for each of the structural parameters. And we are using the same here. In NLME, we just use a ST-PARM structural parameter statement for this. And we also specify these as thetas with times e exponent to eta 1. But you see there's a small difference here. We are just omitting the exponential function if we don't want to consider between subject variability, if we don't consider random effects. And this is a little bit different between these two codes, as you can see. So these are the structural parameters, and then we need to do some scaling because the compartments, there are amounts calculated for each compartment, and here we have some scaling done just between the units. So the volume is divided by 1 log unit, and the same we are doing here. And since NONMEM is doing transform parameterization, we have to put these equations for the microconstants here in as well, just to define those with Q, with a variable flow parameter. And moving on, now we are coming to the fixed effect, the theta table, with the lower boundaries and the initial estimates. So these are all set up here in this matrix, and the corresponding description, what it is. And analogously, very similar in NLME, you have this fixed effect statement, where you just use this vector kind of expression with the initial estimates. We don't need to provide lower boundaries in this case, so the places before the first comma are empty. And what you see here also is the peripheral volume we kept fixed at a value of 480. And yeah, then there we have two parameters here, fixed effects here. These are related to the power error model that you see later. And these are also available in NONMEM. Then we come to omega, between subject variabilities. And here, as we stated, we have 3 random effects on clearance, central volume, and A50. And the other ones we kept fixed. And the same in NLME, PML code, using the RANF statement with these 3 random effects, the variances for these 3 random effects defined. Next, we come to the residual error model. So as I said, we use a power model. This is set up in NONMEM this way, where you fix sigma to 1, and then define the error models using a weight factor. And here you see the power statement with 2 fixed effects, theta 9 and theta 10. And it is similar to NLME. Here we obviously have our error statement, epsilon, and we put everything in the observe statement with this power formula, which is equivalent to this one. Then we just need in NONMEM to specify what is the predicted variable y. This is f plus w times epsilon, and then we need some additional values calculated from NONMEM, like the individual predicted value and the individual residual and the individually weighted residual. This is already calculated automatically in NLME. So that's the code, and yeah, we can start with our first demo. Okay, Shara, can you see the slide? This is Phoenix?
Yes.
Okay. Thanks. So here again, this is a mixed absorption, the Phoenix model. As you know, I'm making this available after the event, and we put a link to the PML School LinkedIn group. You will see it there as well as in the forum. So we've got NLME and NONMEM info, much the same, just a minor difference. We've got some code that we need, the NONMEM code here that you can import from a text file. And this is the code that we just discussed. And so what you can do is you can, when you want to set up this run, you can just send this to a NONMEM shell. I'll just put it into the workflow. So it appears down here. So this is your control file then, and this is a shell where you can set up the run. So you just need to combine your control file with your input, and you see it automatically matches all the required variables, and then you can go and off and run this from within Phoenix, and you get the results back. Obviously, this takes too much time, and I just prepared to run here. So you've got NONMEM here set up in the same way, and as a result, you get some files like lots of worksheets, like for example theta standard errors, omega, and an additional file that I've asked for with all the individual predictions, residuals, and so forth, and all the structural parameters. When you want to set this same model up in Phoenix, you just send your NLME input to a Phoenix model file. And just put it to the workflow as well. And then for the model, you just need also a text file. I mean, we move this one to textual. Remove this text. I'm stealing the code from the model that I've got already here. So this is a code we just discussed. We went through. It's a lot of text around it, as you will see from the original author, Christine Falcoz. Control copy. This is really because the model, you know, there's no built-in function or graphical representative for this, so you just need to deal with the text. So this is it. There are some things you need to adjust here. ID is time is met, amount is depot, and dose is dose. We need to specify some input options. So there are no infusions, but we have reset. So if you want to reset your compartment because you have a second dose after a washout period, you have to uncheck this sort input button, and then you can go back to this input options where you can specify the value of 4, in this case, to reset the compartments. We also got the MDV column at the end that we can match up here, and the information here was given in event ID, and then event ID column. This is reset. So this way now the model looks okay. What are these warnings? Oh, central. Maybe central is amount 1, no, depot and amount 2, yeah, this way. Yeah, now no warnings, and I could execute and it will produce a model of it. The model is already here. You see this here, the results. So here's a theta table, different estimates, and standard errors and CV percentages. You can then go through the different diagnostics and also the actual fits. But you want to compare it as well to the results of these two models. And for this, I showed this several times already. You've got this comparison workflow, and where you just provide data links to produce, for example, a theta table, where you can compare them side by side, or an eta table, where you can compare it side by side. What I've done is I've created an extra plot here, and that's because of the dose covariate. The residual files does not have this information, so I produce an extra table. You can do that in the Phoenix model easily by these run options. You can add a table, provide the times and the variables that you want to see, and then you can use that to plot the data. And here you see the two outcomes. This is for the first ID. You see the fits are similar but different, right? I mean, they are not. They are close, but not too close. So it's a challenging study, the data, and we might need to spend more time in getting the fits, matching closer the observed data. But this is just as a first start. So this is a comparison, and this is what you get out of this mixed absorption model. Let me stop sharing and go to the slides again. So what we want to do with this, I mean, although I wouldn't call this a final model because we are not ready with it, if it's can get improved. I just want to show you, I mean, what you can do when you want to validate your model. And this time we apply a visual predictive check, and for this model validation, it assumes that when you have an appropriate model for your data, your final model that you think of, then a simulated data that you produce with your model should look similar to the observed data on which you built the model. And the simulated predictions will include the whole model. So it will include fixed and random effects. So these are the typical values, fixed effects, and the between subject variabilities, the random effects, as well as the residual error. So it will take the whole model into account to produce this simulated data. And the simulated data and the observed data are then processed by statistical means to show then the distributions where percentiles of the predicted data is shown as lines together with colored bands of the confidence interval of the predicted data. That you see here in this plot. So there are lots of lines. The blue dots are just the observed data. And the red lines are the quantiles, as you see, the observed quantiles of the observed data. And the gray lines are all for the predicted quantiles, and the bands, the colored bands, are the confidence intervals around those. So you see, I mean, this model captured very well the data, not just, I mean, there are some problems at the beginning here, some observed data outside, but most of the observed data is very well covered in this. How do you set this up in, let me show. How do you set this up in Phoenix? So you have your NONMEM model, you saw that in the demo, and what you can do is you can use a PSN shell, Perl speaks NONMEM. I introduced it last time when we ran the bootstrap. This is just a special installation with a bunch of Perl scripts that will process the NONMEM input and output and the NONMEM itself to produce the results that you need. In this case, the simulation and the predicted data. So you just take this, your input file and your control file, and set this PSN shell up. And what you need to do is, here the VPC section, you just have to specify the number of samples that you want to run. And in our case, we want to run 1,000. And that's how you do it. And then you get the results back into, this will launch the scripts, and it will run NONMEM. but it will bring back all the results, the VPC results. This is how you do this in Phoenix. Typically, you'd stick with your model file, the model object. You just copy your final model object and paste it back to the workflow. You go to parameters and fix your accept your fixed and random effects, and then you just switch under run options the run mode from simple to simulation predictive check. Then you have to specify the number of samples under main. You can choose some binning methods like k-means or provide your bins yourself. And then you can choose the quantiles that you want to draw, in the final plot object. So, and then you can specify additional quantiles here. This is how you do this for the Phoenix NLME model. Okay, and then let's go back to the Phoenix. So we are here, we have our final model. What you can do is you can take your final model and send it to a PSN shell. I'll just stick it to the workflow. And here you are. So you have here your file, and then wait a second. This is just a second. No, let me start from scratch. Delete this one. Insert PSN shell, and select the code from this one. And when it sees the code, it looks at the data record in the NONMEM control file and see that there's a NONMEM CSV file required. And so you just bring this in, right? And then this is set up now for execution, and then you can choose Bootstrap, VPC. We go to VPC, and we've got we wanted to have 1,000 samples, so we just change this, and there are some other options that you can enter here in order to set up your command, and then you simply say add to command list, and then it will appear here, and you are ready to go. So once you start, this takes a while, it will launch the Perl scripts and also NONMEM, and will bring back the result, and this looks like that. So this is the same object, as similar, equivalent object. So this is what you get out of these are the results from the visual predictive check, and that's mainly this CSV file where you see this is the information, the outcome of the statistical run on the simulated data. Here you see all the results from that. Okay, and what you can do is, if you are very good at scripting, R scripting, you can use an R script for producing those graphs. So this is coupled with expose, also a set of R scripts that create plots of any kind. You can use this R script here and use that to create some plots, like you just send this one to an R script, just paste it to the workflow, and then you need to select as a source your PSN shell, text output, VPC, and VPC results, right? And then it's set up to create those plots. And this would be, for example, the plot from this run. I have to admit this doesn't look very nice because I'm not that fluent in R. To improve the graphics, I only have used a very simple R script example, but you can easily, improve this plot to make a better plot out of this. For Phoenix, as I told you, I mean, this is much like, you know, the same object is just copied, and I've just accepted all the fixed and random effects, and then went to the run options, changed the run mode to simulation predictive check. Under main, here's the number of replicates. Put it to 1,000. Binnings, I've used k-means. You can use explicit centers or explicit boundaries. And I've checked just the quantiles. And then you just simply run it, and the results are shown here. Lots of output, but this is a plot that you want to see. This is a visual predictive check plot. Typically, you want to see it on a log scale, so let's put it on a log scale. And here you see the colored bands of the, this is a 50%, a 95%, and 5% quantiles, and how it covers the data set. That's how you can run your VPC in Phoenix NLME. Okay, let me stop sharing and go back to the slides. So as a result, here we have the table, the theta table, just as for comparison. The numbers that you see here are similar, but not very close. I mean, in the previous session, we always had pretty close numbers. In this case, because of the difficulty of getting a good fit, these numbers vary a bit. And this is also reflected in the final VPC that we created from NLME and from NONMEM. The observed quantiles are looking much the same, but you know, when you look at the predicted quantiles, the coloring here doesn't. I mean, it looks like it's covering much more space and the higher concentration range compared to the NLME one. That needs to be further examined and adjusted. So that leaves me with summary slide. So again, today we've shown how to set up and run a NONMEM model, quite a complex and a difficult data set of mixed absorption. And I showed you how to set up and run this with NONMEM and Phoenix and NLME, and also how to run this both visual predictive checks for both models. We compared the results, and the estimates are close, but not too close, and this needs further work on getting better fits. With that, I'm at the end of my presentation, so moving to the Q&A session. Let's move over here. Okay, what do we have there?
I think there's only one question in chat.
In chat, okay, let me do that.
Yes. Question is, how did you get F for both absorption?
Let me see where I find this. Sorry, where is it, Sharon?
Did you hear me?
No, sorry. Can you repeat?
The question is, how did you get F for both absorptions?
This is just an estimate, right? So it's you're using different dosings, and you can estimate. I mean, the dosing amount and the from the actual the amounts that are that are presented in the model. Maybe I'll need to, I mean, this is a little bit more complex in this case with F, because it's not typically where you have an IV bolus dose available. Let me respond in more detail in the Q&A that I post on the forum on this one.
Okay, that is the only one.
Okay. Right, and let's, before ending, I mean, just want to raise your awareness to our next session. That is in 2 weeks' time, where I want to show you how to run NONMEM and Phoenix NLME models in the cloud. This is really the current ways of dealing with long model runs, fitting runs. You don't want to spend time waiting on your local PC. You just want to submit it to the cloud, and whenever you have time to analyze the results, you go back and let results synchronize the cloud with your laptop, and you can focus in on the analysis afterwards. This is the topic of next session, running NONMEM and Phoenix NLME in the cloud on May 17th. With that, I'm at the end. Thank you for your continued interest, and hope to see you next time, and goodbye, and you may disconnect now.